Good afternoon, everyone. Today we're going to continue our discussion on machine learning. So let's have a quick review of what we have discussed so far. These are the packages that we are going to use: Quant Mode, TTR, Tidyverse, Caret, very important for machine learning, and the other specific packages for the algorithms. Uh, okay, I don't have the neural net, but later. Okay, then we downloaded the US dollar Philippine peso exchange rate. Okay, also the volatility index data and also Brent. And we said last time that there are missing values and we have to deal with these missing values. We cannot create a machine learning model if there are missing values. So if we were doing, we said if we were just doing a univariate analysis on VIX, which we found out to have 92 missing values, the method of na.locf, okay, where we impute the previous value and uh, and and forward fill it to the missing value. That's perfectly fine. That's the most logical thing to do, and that's okay if you were only using univariate time series analysis. If you were only studying VIX. However, when we have multivariate class, we will have to check if doing LOCF first is better than combining everything first using inner join and then just removing the missing values. And we found out that, okay, so we did the inner join first. Okay, could you kindly check class merge prices? Let's just along the process, let's check if we have the objects. Merge prices contain open, high, low, close, adjusted price of the exchange rate, and then VIX, and then Brent. Could you kindly confirm, class, if you have merged prices, that data, with 2214 observations there? Thank you. Okay, thank you so much for your quick response. Okay, so we have 2214 observations. Now, what we did was we need the returns, class. So what we did was to compute for the returns. And by the way, we said it's better to use the merged prices, the inner join, instead of merging the LOCF process for VIX. We found out that there was not much difference, and doing LOCF will create fake or pseudo values. So we said that uh, since the retained observations were practically the same, so there was no need to do the LOCF. Okay, so we needed to create an object where we had the returns. Okay, so we used quant mode's daily return. Okay, we created these objects. The merge prices is an XTS object. Therefore, what the object that we create here are also XTS objects. So we had the return for USD PHP, VIX, and Brent. Okay. And then also the target variable, which is our dependent variable. We had the next day target plus we use k is equal to -1. Okay, so we merge this returns into one final XTS. Okay, so we have now 2213 observations from 20, what was that? How many for the merge prices? Okay, kindly check class if you now have this the object final XTS class. Final XTS should is an XTS object class. There you go with 2213 observations, because after we after we generated the daily returns, we remove the missing value. Always when you use daily returns, uh, whether type log or discrete, it will generate an NA, a missing value plus, because your data does not have the first row does not have any previous value. So that will generate a missing value. Okay, that's why we have 2213. Okay, and then after that, we created a data frame. Okay, final TBL. Okay, the only difference here is that final table is is a data frame. Okay, while final XTS is an XTS object. So final table class, we extracted the date using the index function and also the returns using the core data. Okay. Okay, so pause for a while. Kindly chat, please, if you have final XTS and final XTS and final TBL. Okay, good, thank you. So let's wait for your classmates, please. Final XTS, final TBL. Okay, good. Okay, thank you so much. Okay, a few more seconds for your classmates. Okay, appreciate class the feedback. Okay. All right, so let me continue now. So the second step we did after cleaning the data, after creating a data that has your returns and your target variable, we said that we will now create an object that contains our independent variable. So we call it feature engineering. So we identified first the parameters that we're going to use. Okay, so we discussed this last time. And fast forward class, first we created this data for fits, which is just the same as final underscore TBL. And then what we did was to populate this with the different predictors or independent variables or features. So we had the lag 1, 2, 3 for the USD PHP returns. We had the simple moving average. We had the SMA long, SMA short. We had the RSI. We had the MACD. We had the what's next? The volatility, Bollinger Bands, volatility, and then of course the ADX also, average directional index. I requested you to do some readings on that for better appreciation of what these indicators, technical indicators do. And then we also renamed our exogenous variable. Okay. Exogenous variable here. We also included volatility class. And finally, the exogenous variable. All right. And let's check class data for fits. Again, let's make sure that we have that data for fits here. 2180 observations. So from 2213, it went down to 2180 because we deleted the NAs, the missing values class. So when you run SMA short or SMA long and appended it to data for fits, there are missing values class for all of the indicators. Okay, so we deleted them, and what happened was our number of observations from 2213, it was reduced to 2180. Okay, so that's now our data for fits. Okay, this is when we omitted the missing values, and then here we generated a vector, a character vector, which includes all the the target and the features. So this is the target class, the dependent variable, and all the 13 other predictors. Okay, so we run this. And then what we did was to create this object final features. Okay, so from the data for fits, which include other variables that were not needed, we just subsetted these variables, key features class. Okay, and then let's just, if I run this class, kind of run it. So you now have you now have your data, your object final features containing 2180 rows of 14 columns. So the columns include the lag return 1, 2, 3, SMA short and long, RSI, MACD line signal, MACD line and signal, Bollinger bandwidth, ADX volatility, and your current, Bix current, Brent current, and your target variable. 14 variables all in all, of which target is your dependent variable, and the other 13 are your independent variable. Okay, so do you now have final features class? Just making sure. Final features. Object, kindly please chat. Okay, good. Thank you. Okay. Thank you. All right. Then what we did, class, we said that the 2180 observations, we cannot use it for creating our model, whether it's LM, RF, etc., because that would tend to to overfitting. So in practice, what's done is to split your data into training and testing. Okay, and when you split your data, there's a difference between splitting your data if you have cross-sectional data, okay, which does not have any time component, or if ever, just a uniform time component. It's data at a particular point in time, okay, versus a time series data. So when we were doing machine learning for classification, we used either the sample function or create data partition from caret, okay, which will generate which will pick values from your data and then split your data into two. For time series, we cannot do that, class. We have to chronologically split our data. So in this code class, we determined how many rows does our object final features have, and we were able to show that it has 1744. So what we're going to do now is to create this object and train. We're going to split our data, and then for train, we're going to use the floor, which means from the earliest date, okay, get and rows times 80% class, 80% of 1744. So if I run this, 80% of, sorry, 80% of 2180 are the number of observations for final features, 2180. You get 80% of that, 1744. Okay, and train class will start from the earliest one, okay, the earliest date up to the 1744th observation. Okay, so having this class, having the number for the train data set, we can now create our train data, sorry, and test data. We use again, the final features object, which contains class all your features and your target variable. Okay, let me just drink water, class. Okay, so final features class we subset the number of rows from 1 up to 1744 class. Take note that this is in order 1, 2, 3 up to 1744. It's not randomly selected, and all the columns are included. Same thing for test data, also subset final features, but this time you're starting with n train is 1744 plus 1. So you're starting with 1745 up to 2180, which is the number of rows of your final features. Okay, so if you run this class, let's just check. Okay, our training data set has 1744 rows, 80%, and then test data set 436, 20%. And again, these are not randomly selected. Okay, it's not choosing number 1 and then number 5 and then number 6, and then in this one, because of the floor function, it's chosen chronologically. Okay. All right. So just to check, class, no? Just to check, we're creating this object the train dates and the test dates. Okay, so if we run this, okay, the dates are 16486 up to 19363, and then for the test period 19366 to 284. Now, you notice, class, that the numbers seem to be chronologically arranged. 1936 up to 2084. And then I discussed last time that the numbers here pertain to the dates, because in R or even in Excel, dates are represented by numbers. And for both Excel and R, the date one, okay, the starting date is 1970 0101. So if you count 16,486 days from this origin, then you'll be able to find how many, what's the date for that. Okay, the benchmark is always January 1, 1970. So here we converted 16486 as that date. We converted this into a date, and the reference is 1970 0101. Okay, so we already discussed this last time. I'll just print it, class. The objective is for us to see when does your train data set start. Okay, let me just, okay, here, class, train data. Wala palang data, no? So, where is it from? Here, class. Okay, February 20. February 20. That's the start, class, diba? February 20. And then the end is 2024, 1237. And then we incorporated this function weekdays to know, class. So 220 is a Friday. January 6 is a Friday. And then here, 0109 is a Monday. So that's that confirms, class, that indeed the split was done chronologically. This is a Friday. January 7 and 8 are Saturday, Sundays, no training there. So that the test data set starts at on a Monday. And then it just so happened that, of course, it's not always a Friday, class. It really depends on the day. Okay, so we discussed already why chronological. Okay, so this is the same train data. Okay, and then we also discussed that we are creating a matrix of your independent variables for train or your features, and then your dependent variable y train. So it's your train data dollar target. For your train, it's also your train data. Then we subset which names of train data minus class, minus, it means do not include target. Okay, same thing with your test data set. Okay, so we ran this already. Okay, we looked at this last time. Okay, so our first model, class, will be linear model. Some of you were my students in FinArts, and you know, class, that linear model, class, multiple linear regression is the tool, is the method used for performing linear regression. Multiple means there are many independent variables. So the equation is this one, okay? Our target variable sub t, because it's a time series, class, is equal to, so these are your parameters, these are your predictors, okay? So the log return, okay, log 1, log 2, and log 3, plus your SMA, smart, etc., up to Brent current, and then plus your residual. Okay, so we said, class, that we're going to, did we discuss this last time, class? Could you please confirm? I think I discussed it in this class. The cross-validation. Yes or no, please? Cross-validation, class. This one, class. I think I discussed this with you. Kindly chat, please. Yes or no? Okay, if you copy this class and then copy paste it here, ito yung class. So may I know, class, if I discuss this with you, the cross-validation technique? Hindi. Okay. Sige, class. Thank you. All right. Let me discuss, class, a very important tool in machine learning. Okay. So just quickly, by way of review, okay, we said that our data class contained 2180 observations. Okay. So this is our data class. This is the clean data. It contains your 13 predictors and your target variable. But we said that we're not going to use all to create our model. We're going to split this into two logically. So this is your trained data set, and this is your test data set. We learned in classification class that you do this class to avoid overfitting. And then the trained data set is 80% of this one, so it's 1744. Okay, while this one is 400 something. So what we do, class, is to generate a model class, whether it's LM, random forest, SVM, etc., using the trained data set. And once we have created that model class in the trained data set, we use that model to predict test data set and also compute for for the metrics, whether it's Ramsey, root mean square error, or R squared, or MAE, or MAPE, whatever the metric is, class. We're going to use the model that we generated from the train model class, okay, and run it on the test data set. Okay, a data that it has not yet seen, that it did not use for training the model class. Now, enter comes cross-validation class. Cross-validation is important because we're now going to generate a model for using the trained data set, which we're going to use, class, for your test data set. However, for using cross-validation class, okay, we will not just use all of this, all of the 1744 observations, but we're also going to split it. Okay, cross-validation means, class, splitting your trained data set and creating folds, FOLDS, class. So it depends on the on the folds. So let's suppose, class, we're using k is equal to 5 folds. So that means that you're going to split your trained data set into 5 sets. 5 sets of 5 folds, class. And what are you going to do with that? So let's go to the let me erase this, class. Let's go to this one. So it depends on what type of machine learning you're using. This is the cross-validation, k-fold cross-validation class for classification. Okay, so what's happening here? So let's assume this is k is equal to 5. How do I know that this is 5? Okay, it's called five-fold cross-validation. Okay, how do I know, class, it's 5-fold cross-validation? Take a look at this, class. So fold 1, fold 2, fold 3, fold 4, fold 5. Okay, so what happens, class? Okay, take note here we're using the trained data set, the 1744. Okay, assuming that we're using our problem is classification, class, no? But take note our problem is regression. Huh? So what happens? Just to point out, class, the test data set is totally not involved in your cross-validation. It's only the trained data set. So here we're going to create an in-sample, we call it in-sample, inside the trained sample class, we're going to create a test data set. Okay, so what happens? We can split it equally into 5, and then we will now create, let's say you're using random forest, okay, or LM or whatever algorithm you're using. We will now create our first model. Our first model class has this as our train, and then a certain portion will be used as a test data set. So we're now going to create a model, okay, let's say random forest, and measure, let's say RMSE. We're using root mean square error. We're looking at the the capability of the model to predict our test data set here, class. This is our, in this case, oops, my mouse is test data set. Okay, and then next, class, what happens? We use the next split. So again, this is our train data set. The next group will now be used as a test data set, and this one will be train. So once again, we have 4 trains, okay? This train data set, and the other one is test data set, class. So this will now create another model, and then we're now able to compute for the Ramsey. And you go on, class. This will be your test, this will now be your test, and this will now be your test. So you can see here that all the observations will have an opportunity to become part of a test. Okay, so RMC here, RMC here, RMC here. So we have 5 RMCs because we have a 5-fold cross validation. If it was a 10-fold cross validation, class, then we have 10 splits here. Okay, and then what do? We get the average of the Ramsey here. So Ramsey, and then we get the mean of the Ramsey. And then we also get the standard deviation. So what's this used for? This is used for determining, okay, the final model, class. So you come up now with the final model, and then, okay, we do it for the whole training data set. Okay, this one, the 1744. So in other words, class, you're creating 6 models. Why 6 models? You have 5-fold plus the final model, which now includes all the training data set. Okay, for the 5-fold class, you have 5 splits. Okay, 5 splits. Okay, so each of the split class will contain a testing data set, and it will contain also a training data set. So this is what's used, class, for classification. But the same cannot be class for time series. Okay, because, for example, here, this is our test data set. Let's assume this is chronological, class. So what we're doing is we're using this data in order to predict this data. But how can that be? You already have future, as regards this split class. Let's say this is January, say this is January 1, 2020, let's say 2023. And then you have here December 3, 2024. How can you predict, class? You have December 2024 here. You're using this as your training in order to predict January 1, 2023. How can you predict, how can you create a model using the future value, okay, in order to predict the past? Okay, and that's what we call a look ahead bias. Parang we looked into the future to try to predict the past, especially considering that the data could be correlated. As you know, class, the order in a time series is very important. It's logical. So this is okay, class, for classification, but not for regression. So for regression, what happens, class? Okay, let's go down here. For regression, this is what happens. Okay, take a look at this, class. It's quite different. Okay, so let me explain what happens cross-validation, class, for time series. Okay, so what happens here, class, is that we split our data. The splitting could be equal or not equal, no? But what's important that, okay, so for example, we split here. So this will be our first train data set. And then this one will be our test data set. So we're not using everything, class. We're not using everything for the split number 1. Okay, we just use a portion. Okay, so the next one, the next split class will be, we now include both of this. Okay, so this now becomes your train data set. We now combine these two. This will now be your new train data set, and then a new test data set. And the test data set will oftentimes be equal to this one. Okay, so for example, this is 200 observations, and this is 50 observations. Okay, take note that we're not using all the data in the train data set. So the next split now will be how many observations in the new train. 200 plus 50, 250. Okay, and this one will be a new 50. Okay, why is this so? So that, class, your test data set, okay, what you're going to predict, class, using your train data set, will always be in the future, class. Okay, so the 50 here will be in the future in reference to this one. Take note, I'm not using the data here to predict, class. I'm not using this as a train data. Cannot be, class. Cannot be, because I cannot use this as a train and predict at my test data set here, class. Okay, so this is called your rolling window. So in the next class, in the next split, what happens now? So for the next split, it will now be, we now combine this, class. So this now becomes 300, yes. And then the next 50 here. Okay, so until such time, class, that you're able to complete everything. I'm just giving an example for this is what we call, class, the initial window 200. Okay, and there are certain guidelines in order to choose how many will be our initial window, class. This is called your horizon, class. And usually the horizon is the same. It's constant. Let's say 300 each. So you keep on moving 300, 300, 300. Okay, so this is your walk forward method. And each time, class, you notice that your test data will always be, quote unquote, future in reference to your train data set. So that's how you do this, class, and complete the 1744 observations. Okay, so it's like creating a model within a model. Okay, so and again, class, please take note that your test data set, your 400 plus observations, is not involved here in the cross validation. Okay, so once again, as discussed a while ago, you have your Ramsey here for the first split, Ramsey for the second, third, fourth, fifth, and then we get the average of that, and then get the standard deviation, and then R will now generate the best model. Okay, and then it will now run that model to the whole training data. And once we have that, the result, after we use that model for the trained data set, class, we now use it for the test data set. Okay, so let me pause for a while, class, and check, class, if you're able to, if you understand, class, yung cross validation, class, very important in machine learning. Okay, thank you. Moises, how about the others, please? Okay, good. Okay, so that's something you should not forget, class, when you're doing machine learning, yung cross validation and okay, all right, good. So I'll explain in a while how that cross validation will now be used for all the algorithms, whether it's LM or random forest or XGBoost or SVM or ANN, class. This same cross validation will be common to all, class. It will be common to all. Okay, so let's now take a look at what we're doing here. Okay, go back to our R class. Okay. Okay, so I just explained to you class why we need the walk forward validation class, no? Cross validation for time series, it's specifically called walk forward validation or rolling origin validation class. Okay, and it's in order to avoid, I mentioned this a while ago, look ahead bias. Okay, imagine trying to predict a date in the past class using a date in the future. How can I use, let's say, data from March 5, 2024 in order to predict data from February 1, 2023? It doesn't make sense, class, no? Diba? Kasi technically, class, March 2024 data should not have happened yet when you're trying to predict your February 2023 data. Okay, so that's the main let's say main principle there. Okay, so here class, let's now set up our initial window. You have to understand this class. Number one, okay, we identify our folds. Usually it's 5 or it can be 10 class in other instances. Okay, and then here initial window class. The initial window is the number of observations that we will first use class for our first split class. So how many observations? Okay, I said that it's not necessarily 1744 divided by 5 because we have 5 folds class, right? Not necessarily, but rather we use a certain benchmark. Well, we use either 30% of your trained data or 100, whichever is higher class. Okay, so 30% of your trained data, okay, our trained data is 1744, remember, okay, 1744. 30% of that and compare it with 100, so that gives us now, the larger one will be your initial trained data, okay? And then we compute for the horizon. The horizon class is the number of walk forward, our test data set class. Okay, that's what we defined as 50 a while ago. So easily that can be done class with this formula. Horizon is equal to, again, from floor, okay, the number of train minus the initial value over k minus 1. Okay, so here we also have a condition that if the horizon is less than 1, okay, stop already, because the horizon, so what you're adding to your current train data cannot be negative class. Okay, so let's run this class. If you run this, let's run this code chunk, you'll now have our train data set is 1744. We know this already. Our initial window is 523. Okay, so the first observation for your training, for your split number 1, how many splits do we have? We have 5 splits class. Okay, why 5 splits? Because this is a 5-fold cross validation, and your horizon will be 305. So the first 523 observations will be your first initial training window, okay? And then the testing will be 305. And then what happens next is that you add 523 with 305, that will now be your next training window. So that's what happens here, class, no? Okay, we slice now, we use this function, create time slices from 1 up to n train. So we identify what's our initial window. Our initial window is here, class, okay? And then we also identify the horizon from above. And then fixed window class means, okay, fixed window is equal to false, means your training window will not be fixed. It will keep on expanding class. All right, and then we also run this class, okay? All right, so let's run this class and I'll show you class. Okay, so run this class and then run this. That will now create the slices, and then here class, we will index the slices here. Let's just run this. And then here class, take a look at this one. We're now going to specify class, ano yung slice for training and for testing. K stands for, di ba, 1, 2, 3, 4, 5. So what will be the first train for uh, uh, fold 1, for slice 1? What will be the next for hanggang 5 class, na up to 5? So let's run this and let's see how we're slicing the data. Here you go, class. So this is how we slice the data. Okay, for the first fold, class, for the first slice, we said that the number of observations for your train is 523 here. So the first 523 observations, this will be your train, and then the next 305 will be your test. 305 here. 305. So what will happen here? Create a model using this, and then predict using this data. And then you'll have a value for your RAMC. We will measure the error term using our test data set with the model that we generated from this training data set. Okay, so we have our first RAMC here, root mean square error. And then let's go to the next fold, class. Our training data will now be 828. Where did that come from? You now add this, class. Okay, the original test data set will now be added to your train data set here. So our train now becomes 828. You now have a larger training data set to create your model, and then we will now use it for our next test data set, the next 305. Okay, so your horizon will be the same, class. 305, 305, it will keep on increasing by 305. So this is the next 305 observations. And once again, class, please take note that the values that you're using here are past, PAST, compared to the 305 here. In relation to the 828 observations here, these are future yung 305 na to. And then you keep on going. No? Yung susunod, the next 1133 observations, you generate now a model using the test, the next 305. So your test rows remain the same at 305. And you keep on generating a RAMC, root mean square error. You compute what's the root mean square error for fold number 2, fold number 3, fold number 4, up to fold number 5, class. Take note. You use 1439 rows of observation, 305. Okay. If you add this to, class, it's 1744. Okay, so you will have five folds, class. Okay. And then what's done is you get the average of this RAMC. So you have your average, mu, and then you have your standard deviation of your RAMC. And then R will now generate the model, class, based on the inputs of your 5-fold validation. Okay, and then it will now use that model to run 1744 observations, the whole train data set, class. And then it will now be used in order to predict the test data set, class. The test data set, okay, not this in-sample data set, but rather the original test data set, which is not part of 1744. Take note that these test rows are part of 1744, class. Okay, so does that make sense, class? I'll pause for a while and kindly chat, please. I hope everybody will give their feedback. Is that clear, class? Yung rolling window, okay, or walk forward cross-validation natin for time series data. Hello, class. Feedback, please. Okay, good. Thank you. Any questions, class? Please feel free to ask questions. Huh? Okay, good. Okay. So you have the pattern, class, for your case. No? It will be similar to this one. It's a group case. Okay. All right. So we move on, class. Okay, Okay, now this is very important. Okay, we now make use of the caret function, okay, in order to create our model. Now, this model class will be used for all the algorithms, whether it's random forest, it's XGBoost. The only difference class will be this one, the method, and some parameters class. Here, method will be the same class, okay? Okay, let me first explain this, what this is class. So where you're creating this object, TC custom, okay, and so we will be generating this, no? TC custom, which we'll be using for all the algorithms, machine learning algorithms. So trainControl, it's a very powerful function class from the caret package. It will control how models are trained and evaluated, especially during resampling or cross-validation class. So our resampling is CV. This is our cross-validation, the one that I showed a while ago. And remember, class, index is equal to train list K. Okay. Remember, class, this is our training class. Index out is our testing class. Okay. The K stands here for the fold. Fold 1, fold 2, fold 3. So if you have 5 folds, then this will become 1, 2, 3, 4, 5. Just like what we did here, class. Okay. Okay. And then here, class, save predictions is equal to final. What's this class? This class is the model for the whole training model, the 1744. So it will not only come up with model for fold 1, fold 2, fold 3, fold 4, fold 5, and also technically for fold 6. Okay. Fold 6 is when you use all your data class, your training class, your 1744. Okay. So we said that if it's a 10-fold cross validation, then you'll have 11 models. Okay. For fold 1 up to fold 10, and then fold 11, the last one will be you use all your training data set. Okay, so that's what we mean here by save predictions, final. Okay, and return resampling class. It's but every time we have a model for each fold. Okay, that process is called resampling. Okay, so the resampling class, it will have its own Ramsey, for example, it will have its own R squared. So it will also save each of the, for example, here class, our model will create the Ramsey, it will save the Ramsey for fold 1, the Ramsey for fold 2. So everything will be saved class. So this is a very powerful one. And then, okay, so this one will be defining our TC custom class. Okay, and then we're going to use that here class. trainControl is TC custom. It's the one that we mentioned above class. Okay, so this is now the model class for linear model. Let's call it LM time aware. I should have used LM underscore model. Okay, to make it more simple. But take a look at this one class. The function is train. Okay, what is our dependent variable? Target. Associated with here, that class. It means all your predictors, all your features will be used. What data? The data will be our training data class. What method? LM. This is where class the different algorithms will change. So if you're using if you're using decision tree, you can put here R part. For random forest, it will be random forest, XGBoost, etc. Okay, but we're using, okay, we can change the name here, of course. We're using the same trainControl because the trainControl has been defined above. Okay, so that we will have now a good comparison class between the different models class. Okay, so for this one, I think I added some notes here, class. Kasi here I mentioned center and scale. So what do you mean by center? This is a good practice where all your predictors class, we will subtract the average class. Okay. if we subtract all the respective averages class from each of the observations in your feature class, let's say RSI, if each of them you subtract the average, and then you get the average class, the average will be equal to 0. Okay, so you're changing the average now. You're making it 0. That's what we mean by centering. Okay, we center our data and make sure that the average of your observations is 0 for that specific variable. So that goes to show that goes for all the other variables also. And also for the scale, we divide each of the features by its standard deviation. Okay, so if you divide everything by the standard deviation, so for example, the x minus x mean over sigma, okay, isn't that normalizing your data? And that will make your standard deviation equal to 1. So it will make your mean equal to 0 and your standard deviation equal to 1. Okay? All right. So that way, class, yung mga our independent variables are all centered and they're all scaled so that the comparison among the algorithms will be the same. Okay, so let's run this class. Let's run our LM time-aware model. And the summary class, the summary for the model is, okay, take note of this class. So we now have the log 1 is significant, log 2 is significant, log 3 is not significant. We have here some variables that are significant. SMA short, SMA long, RSI, MACD. Okay, but for us, what's most important is this. Okay, multiple R squared, 5.26%, adjusted R squared, 4.54%. Okay, it means that our model is able to explain only 5% of the variability of our target variable, which is our target, 5% lang. And this is the model for the trained data set, no? So we will have to run this model class that we generated, this LM time-aware using the test data set. Okay, I hope you're not lost now in the details. Okay, I hope you're not lost in the details. We're now using the model that we generated using cross-validation class for our LM class, linear model. Okay, making use of the TC custom that we developed above class. Remember the cross-validation, the index and the index out where we split our data. Okay. All right. So now, class, let's first take a look at the object LM time aware. Okay, if you have done linear regression in R, okay, you will see that this object, it's a list. Okay, it's a regression output, but okay, let's run this class. Take a look, class, at our time-aware object. You notice that compared to just the ordinary LM, where you don't do cross-validation, this has more. This has more output. Dun sa, if it's only regular LM class, you don't have a resample here. Take a look at this class, resample. There. So you can see here, Ramsey, and there are 5 Ramseys here. So remember, you have a 5-fold cross-validation, right? So this is the Ramsey for the first validation. This is the second one. This is the third one. This is the fourth one. And this is the fifth one, class. Okay, also R squared. Also MAE. Okay, and you can see here the resampling class, if you recall, up to 523, observation 523, and then up to 5828, and then up to 1133, okay, etc. Okay, so also here you have the final model class. If I click this, okay, so what's this class? This final model class is now the regression output where we used all the observations in our training. It's this one class, yung final model, this one class. So you can see here that the LM results with cross validation is much more powerful class than. Okay, let's just do this for purposes of comparison class. I'll use an object called let's just use mod LM. Okay, alt minus, and then let's use the LM function, and then target. Okay, tilde dot. Okay, data is equal to train underscore data. Okay, so if we're going to use R in order to generate an OLS, okay, this is the model class. LM independent variable regress on here. That here means all the independent variables, and then identify the data. Okay, and then let me just shift enter, get the summary class. Summary of mod. I just want to compare class. So this one, we're not using here the cross validation class. This is an ordinary LM model class. If I run this, okay, take a look class. And let me run it again. Arrow up. Okay. You can see here that you can compare class. You notice that the results are quite different, but the R squared is just about the same, 5%. Okay, adjusted R squared is around 4.5%. They're about the same class, but what's the difference class? If you take a look at the LM model here, let's go here class. LM model, it's also a list class. LM model, letter L. What did I call it, class? Okay, what's that? Mod LM, sorry. Mod LM here, class. Okay, mod LM. Okay, look, class. The elements of mod LM is far smaller than the LM time-aware class. When LM time-aware, we incorporated cross-validation there. Here, now there's no resampling here, class. Because in the mod LM class, it just makes use of the trained data set, everything there for your ordinary least squares. While on the other hand, ito class yung my cross-validation here, LM time-aware. Take a look. In fact, I pointed out to you, class, this resample. So we can extract the Ramsey for each of the folds, class. And of course, for the final model here, here, class. Okay. Okay, so let's so far clear, class? May I have your, okay, may question ba dito? Yeah, okay. Yeah, Paula. No problem. Okay. Your confirmation, class, your comments, if you're able to follow, class. Okay, good. Thank you. Should you have any questions, class? Please feel free to ask them. Let me just close some of the. Okay, so let's go back here now. Okay, so we're done with the LM class. Okay, let's just have some more discussions about LM. Okay, so this is the result of our LM class, 5.25% R squared, 4.54% adjusted R squared. Okay. So I told you a while ago, class, that we can, what's happening here? You can get the per slice resampled metrics class. Okay, this is our model LM time aware. And then we can get the resample class I showed you a while ago, class. Okay, then we can get the RMC, RMSE class. We can get the results class here. Okay, so let's just print this. Okay. So here are the values class for your RSI. Okay, the values of your parameters class. And then this one is the value of your RAMC. Okay, how many folds? 1, 2, 3, 4, 5. 5 folds. RAMC R squared MAE. And if there are intercepts, yes, true. And these are your resampling. Okay, so we can extract this metrics because we did cross-validation, and for the cross-validation, we use k is equal to 5. Then we'll have 5 measures for RAMC, for R squared, etc. Okay. Then we can here, class, we can actually compute the mean as manually. So here, for example, mean R RAMC is equal to the mean of your, this is our model class. We can get the resample and then get the RAMC. Okay, so you'll have the average of all the RAMC, the average of all the R squared, okay, and also the standard deviation. Okay, so let's run this. There, class. The average RAMC is around 5%, okay, and the average, the standard deviation, not the average standard deviation. The standard deviation is 0.008. Okay, R squared on the other hand, the R squared, the average is 1.26, so it's quite low. It's only able to explain 1.26% of the variation of your variable target. Okay. All right, then let's extract the final model class, yung summary ng final model. So we already generated this above class, 5.257. Okay. The final model. Okay. So all right. Now, of course, this result class is on the trained data. Okay, but that's not what we're interested in. We want to know how good your model will be on our test data class. Diba? So if you recall, class, what we do is to create a prediction for the test data set. So predict, class, if you recall this, predict using our model, but this time our data will be the test data. Okay? Okay, so this is more important, class. This is the acid test. How well does our model work, class, with our test data? Okay, so let's just identify our actual data. Okay, is our test data, and then let's get target. Let's call it observation, obs data. And then here we're creating this, this is just a function class where we're getting the average. This is your RAMC class, yung average of the actual value minus the predicted value squared, and then get the square root. Also the computation for your MAE, and then your R squared. So we're just first, and then I added here a directional accuracy. Okay, now this is very important, class, because it will now compare the mean of the sign of your observations with the sign of your prediction. It will what directional accuracy will compare is that because sometimes the values, the predicted values might not be as important as comparing it with the direction. What do you mean by direction, class? For example, did the returns go up? And was the prediction, class, up also, positive? That's what I meant. Direction, positive, positive, or positive, negative. So how many times were the prediction wrong? How many times did the actual returns go up, which means positive returns, okay, but the prediction was negative? Okay, so we're measuring, class, directional accuracy. And we want, even more important than the R squared, is how many percent of our prediction were correct. Were correct in the sense that the returns were actually became negative, and the prediction was also negative. The returns were positive, and then a particular return was predicted to be positive. So what's not good is that the return of a particular day was negative, and then the prediction was positive. So that's what we mean by directional accuracy, and we're also going to measure that. Okay, so here I made some notes. If the directional accuracy is equal to 0.5, then our model is no better than just coming up with a flip coin. No? So this flip coin, will the return tomorrow be negative or positive? Maybe negative then, because it's just 50-50. So we would want the directional accuracy to be high, greater than 55%, or maybe 60%. Okay, higher than 55%, higher than 60%. If the directional accuracy is less than 0.5, it means that most of the time the model got it wrong in predicting your returns, whether it's positive returns or negative returns. Then this is worse than doing a coin flip, because in a coin flip, class, you have 50%, right? That's heads positive, tails negative. So if we just use a coin flip to determine if the returns will be positive or negative, then you still have a 50-50 chance of coming up with correct predictions. Okay, so let's run this class. Let's run this function. Okay, and then we go here now. Okay, let's now compute, class. Their model is our LM time aware. So let's compute for the Ramsey, MAE, R squared, and then directional accuracy. And then let's print it. And let's see, class. All right. So this is the result for our, okay, this is the result for our test data set, class. Okay, the Ramsey is 0.004. Okay. The we have a problem here. The R squared is negative 23%. So not good, class. Not good. If you have a negative R squared, class, it means that you're far, far away from on the average, your prediction is much worse than just getting the mean. Okay. The directional accuracy is more or less 50%, class. So it's just 50-50. Okay, so this model, class, our LM model, in predicting our test data set is not good, class, because of the negative R squared. Okay, and I made here some comments, class. It means that a negative R squared, our model performs worse than simply predicting the mean of the target variable. So why don't we just get the average of the target variable? And then just every time, every day, our prediction is just the average. Keep on predicting average every time. Okay, but what's happening here is that you have negative R squared. Oh, this is bad, class. Okay, so it means that our model's prediction are on the average further away from the true values than if we have just guessed average return every single day. Okay, this is a clear sign that the model has failed to generalize to the test data. Okay, so as far as the LM model is concerned, not good because of the negative R squared. So if we just, let's print, class. Okay, let's plot. Yeah, just highlight this, Control Enter. Take a look at the plot, class. You can see this is our prediction, and Okay, you can see the actual value, and this is the predicted value. Okay, so very bad, no? Very bad output class. Okay, so let's just to summarize class. What's the process above? We have the cross-validation phase class, okay, where we use cross-validation in order to do resampling, where we split our training data into several folds, okay, and then after that class, we generate our final model, and then we predict class using the test data, okay. So this is the structure class that we did class, okay. After we split into train and testing, we performed cross-validation on the training data, okay? And then after performing cross-validation, what do? We were able to generate the final model using the model itself class, and then we test our model for using the test data, okay? So that in a nutshell class is okay. So this one class, I just put together all the codes that we did class here. So up to this part, this is what we did just now class. Okay, where we identified the initial window, the horizon, then we sliced the data, and then we determined class what's the first fold, second fold, and then we run the model class. Okay, and then compute for the Ramsey, MAE, R squared, and then also the direct accuracy. Okay, for the next one class here, we're now going to our ML models class. Okay, so please run this. I'm adding here IML, fast SHAP, and SHAP Beast. Okay, we're going to use also SHAP. Okay, could you kindly run that, please, class? I have just a few more minutes, and hopefully we're able to. I'm going to show you, class, the other models, okay, which are these ones. At least I'm able to show you, class, what's happening to the other models. Okay. All right. Have you run this class? Have you installed also IML, Fast SHAP, and SHAP Beast class? I'll just extend a little bit, class, if you need to go, just for recording purposes, class. Please feel free, you don't have to ask permission. Okay. Because the next part are the model for decision tree, random forest, for support vector machine, for XGBoost. I have here some notes, class, for XGBoost because it's quite a the output are actually quite long. Okay, so I included here an explanation for the output to guide you in understanding what happens to XGBoost, and lastly, your artificial neural network. Okay. All right, the last step will be now we compare all this LM and the other 5 models class. Okay, so let me point out to you, class, that please run these models. Okay. So this one just tests if you have your trained data and test data. Just make sure that we have them. And then here again, make sure that the packages are loaded. Okay, so first we have our decision tree. We already have run this in classification. Okay, and so this is the code class. So this is our decision tree for our training data set. So we first run our algorithm for our training data set. Again, set that seed, and then the same function class, tree model. Okay, we call it tree model. A while ago we called it LM. Train, and then target is the same, target, and then tilde, then all the predictors. Same data is equal to train data, and then take a look at this one, class. We're using R part Okay, let's use our part. A while ago, we used LM. So this is where it will differ. No? And then same pa rin yung pre-process, same yung TC custom class. And then here class, it will differ here. We don't have tune length class for LM. For random forest, we have. Okay, so we're including more tuning for this one. And then the metric is also the same, R, RAM-C. So let's run this class. Okay, and then you have the result for the training data set for random forest, for decision tree. There you go, class. 1744 samples, 13 predictors, class. And then you have here, class, we're using 7 class tuning, no? Tuning. So we're having seven tuning here. RAM-C, 3, 4, 5, 6, 7. R squared also 7. MAE, 7. Okay. And then we also have a final model here. All right. So, and then we go to, you do the same for your random forest. The only difference is that here you're using RF and we're changing the name, RF model. Okay. Also, tune length, we're using 5 here. And 3, we're defining it to be 200. So those are the differences between just the tuning differences because each of the algorithms class will have their own unique characteristics. Okay, so this is not the same as your LM. Okay, so these are just some of the nuances, but the rest are the same. Okay, still TC custom. Okay, still RAM-C. So let's run this class. Okay, and then we have now our result for random forest. What I'll provide you with class is just the summary of all of this and comparison. Okay, while it's loading class, you also have support vector machines. I gave here some very brief discussion. And then what's different here class? SVM radial here. The method will be support vector machines. Okay, TC custom still the same, preprocess, center, and scale. Metric still the same. So what the good thing here is that we were able class to come up with a TC control, TC custom for all the models. And then we're using it here. Okay, TC custom includes your cross validation and it will be common for all. All right, so you have here class for your random forest. Okay, your R squared, it's lower than your LM, okay, lower than the others. Okay, so you can see that the RAM-C is higher, which means that the other models are better. Okay, we're going to compare that. And then SVM class, again, run this. And then it will now print the model class. Now take note, all of this class we're using for train. We're only using train yet. We're going to run the test data set. Okay. So same thing class here. Our tune length is 7. Okay. And then we have the R squared here. If we're going to base it on R squared, then this is lower, also 1% only. Okay. And then this one class, XGBoost. Okay. Now take note here. This will take 2 minutes class, and the output is quite long. So I already gave you here some explanation about the output. And what's different here is that I use TikTok here in order to count how much seconds it elapsed. So a while ago it was around 2 minutes plus. Okay, so here this one class you can also use instead of TikTok, you can use start time and then here end time. So you can uncomment that, which is what I use here class for ANN, artificial neural network here below here. Okay, start time ANN, you have processing time because ANN is also quite long. All right, so please run XGBoost. Also run ANN. You have the codes already there. And then I will continue the comparison. That's the last thing that's lacking here, class. The model evaluation and comparison. Okay, so at least we have already LM, we have decision tree, we have random forest, we have XGBoost, and we have SVM and ANN. Okay, and then I'll just record the remaining portion. I'll give you also the remaining remaining codes. Okay,